Welcome back to another lesson with me, Mr. Wong. Today we are looking at Module 7, Nature of Light. We're going to be investigating spectroscopy, how that tells us elements of the periodic table, or how to identify elements of the periodic table. We're going to then use the spectroscopy of stars to find information about their surface temperature, their rotational and translational velocity, their density and chemical composition. Okay, so let's firstly recap on how we can use spectroscopy to identify elements. If you remember, if we have a light source, we run it through a diffracting gradient. So this thing we have here is called a diffracting gradient, and that essentially diffraction gradient. This little slit here helps focus the light beam and helps us focus on what we're trying to look at when it comes to light. If you have a look at this here, the continuous spectrum, all major light sources, the old incandescent light bulb, the sun, they all create this kind of continuous visual light spectrum. If you run this source of light through a gas, okay, you'll come across a thing called absorption spectrum. So what's actually happening in this gas is it's absorbing some of the energies going through the EMF. So some of the energies from this color spectrum is being absorbed by the gas, and the reason why you see these little dark bands in the absorption is because of the absorption of energy. What also happens is once the energy has been absorbed by the electrons moving up different states, so if you recall, there are different energy states on an atom, so say 3 and then 4, and then you have the center of the atom here. Okay, when absorption occurs, it takes the light energy, takes some of that light energy, the electron goes from here, goes up, absorbs some of that energy. That's explain the dark bands here. If the electron wants to come back down, okay, if it wants to decide it's had enough of a good time, it's more than enough excited, and it wants to come back down, it needs to lose energy, and it comes back down like so. But for it to lose energy, it releases it in the form of some kind of electromagnetic radiation, in this case, usually visible light. And what you see on the right here, the entire spectrum, or all the different spectras, these are the kind of light sources that hydrogen, helium, argon, these are the type of wavelengths of light it would release back for when the electrons go from a higher energy state level to a lower energy state level. The concept of how temperature and color are related were first really investigated by Kirchhoff and Bunsen. Bunsen as in the guy from Bunsen burner. And they came up with a very simple demonstration where they tried to heat objects up and have a look at its color spectrum. And we talked about before with flame tests. So these were the main things they were doing. They were doing little flame tests, and they found that different flames gave off different colors, which is pretty in itself, and so on and so forth. Like I said, for an electron, when it goes up, once it's relaxed, it wants to fall back down to a lower energy state. This is being a quantum thing where electrons can't be excited forever. It wants to come back to its original level. And so each electron belongs to a discrete level. This is the reason why we have different flames for different elements. It coincides with how much the electrons get excited and then how much more relaxed they feel after that. Bunsen and Kirchhoff also found that temperature, or at high temperatures, it doesn't really matter what the chemical composition of the element is. So at high temperatures, so at high T, basically the color doesn't really match with the chemical composition anymore. which is something we talked about. Chemical composition does match with color under low pressure or low temperatures, but at high temperatures, it doesn't really matter. As a matter of fact, it kind of goes from yellow, and then it goes, it goes from red, and then it goes to orange, and then it goes to yellow, and then it kind of goes white as the temperature is increasing in this direction. So they kind of found that temperature had a major role in the color you see on an object if it was really high, okay? And also one other thing I glossed over is this part here, the glowing effect. So there was this idea if you could heat it further, it would kind of glow UV light or electron or X-rays, which we later find out that's not really the case, but that was what they were theorizing based on these investigations. So what were their findings of these two? So you could produce a continuous color spectrum, so like a whole rainbow of dense gas like the sun, which also produces a continuous spectrum. If a gas exists between the light source and the spectrum, or the spectroscope, light is absorbed from the continuous spectrum at wavelengths or color characteristic of the chemical components of the gas. So basically, depending on the gas you have, it will absorb a particular color or particular wavelength from that rainbow spectrum, that colored continuous spectrum. And the dark bands you see, the absorption spectrum, is the specific wavelength in which the absorption occurred at. Next, a glowing gas produces bright lines on a dark background at wavelength or colors of the components of the gas. It shouldn't be of gas, but of gas. If I just correct that quickly. Basically, that's to say the emission lines, the emission spectrum you see is also dependent on the energy transitions back down from an excited state to a less excited state for gas as well. So that's quite a lot to compact straight away. And so the first person that actually used Spectra in a way to help identify an element of the periodic table was Joseph Norman Lockyer. Finally, there's a name of a scientist I can pronounce properly. So he detected the Fraunhofer lines in the solar spectrum, and he found these particular lines here. So he found that. And he noticed that these absorption lines didn't match with anything that they knew of the elements of the periodic table at the time. So he called it the helium atom. So he said, we don't have this. This probably does exist, but there's no way to identify it just yet. So he made it a core and called it helium. Why helium? Well, this is where the whole Greek thing comes into play. So in Greek, helios means the sun. So that's why he called it helium, to name it after something he was investigating through the sun. Not that he was looking directly at the sun, I hope not. William Ramsay isolated the gas of helium in a laboratory, and he found that the reason why why it was so difficult to find helium initially, one, it is an inert gas, but two, it has such small mass, it's not going to sink to the bottom. It's actually going to rise above air, and it's going to be really hard to contain it within the atmosphere. So that's kind of why we can't really detect helium that easily, and that's why your helium balloon kind of floats up very easily. Okay, so let's try and picture the color shifts with this little orbital diagram that I've shown you before. So electrons move to an excited state. What goes up must eventually come back down. They will relax and go back to their original lower energy state. But in order for this to occur, they have to release energy to their surroundings, because each energy level has a discrete number. And an electron can only be in this level if it has a certain amount of energy. If it has too much, it's not going to be able to be in that. Okay, so the larger the shift, let's say from 6 to 2, the more energetic the colored light will be. So we know on the electromagnetic spectrum, or the rainbow spectrum, we know that blue light has the most energy because it has the shortest wavelength. So from 6 to 2, it's most likely blue. And then the lowest energy transition, 3 to 2, that associates with red light here because it has the lowest amount of energy. So what kind of value do we get from using this to identify elements? Well, we know that electromagnetic radiation passing through gases, some of that color or electromagnetic radiation will be absorbed by the atoms of the gas. Now, depending on the dark bands of the spectrum, we can identify the wavelengths absorbed there. Okay, so the value that has is each element has a unique code of electromagnetic radiation it will absorb. Okay, so now that we know that each element will only absorb a specific type of radiation or wavelength or types, a little code of that, a little pattern, we start seeing little patterns forming where the energy difference of the electron shifts between these levels. So each element has a unique pattern of radiation it will absorb. So if we know what that pattern is, we can look at other objects using spectroscopy to locate the types of elements that might be in the substance we're looking at. And that's a very powerful tool. So spectroscopy is the study of interactions between matter and electromagnetic radiation. We can use this to identify elements of stars, which is kind of how we worked out that most stars are made up of mostly hydrogen and mostly helium. We also know that with radio frequency spectroscopy, we can actually use this to visualize internal soft tissue injuries of the body with incredible resolution. We can use microwave spectroscopy. That's with black body radiation. So this is kind of more with the origins of the universe and the Big Bang. But as you can see, like the little emission bands from each element gives you a really unique sense of how each element has its own unique bright spots and dull spots. If we have a look here in one of the questions, I won't go through them today, so you'll have to solve for yourself. We have 5 elements shown. Which of these would be in the sun's composition? So if I have a look here, so this is the sun's spectra, and let's see what kind of elements match up with it. Well, we have hydrogen that kind of fall under the similar spectra to the sun. We have helium that also kind of falls under the same spectrum. So this kind of gives us an idea of where the transitions are occurring. You can see that there are some iron, calcium, and sodium. Some of that does kind of mix and match kind of with the sun's spectra, but you can see majority of these are quite hit and miss. There's definitely no iron really going around here. Very low numbers of calcium. So the most likely answer is we have mostly is hydrogen and helium as the chemical compositions of the sun. Question 2, we're looking at the spectras of hydrogen, helium, sodium, calcium with star A, B, and C. And then we look at question 3, which of the elements shown are contained in the unknown substance? So another thing to look at here. Okay, so that's pretty much it of how we can use Spectra to identify elements. Let's look at other information it can tell us. Let's say surface temperature, rotational and translational velocity, density, and chemical composition. So have a look at this. We actually find a unique case, the OBAFGKM. So this was an old labeling symbol they used to do with the brightness and the size of the stars. What you can see here is the higher the value of K, so the higher the temperature, the more blue or the greater intensity towards the blue side of the visual spectrum we see. Now, the really, what would you call the lower temperature stars? They favor more the red colors, and the higher values of temperature favor more the blue colors. Now, one thing to make very clear though, as you can see in the 6000 Kelvin, there is some blue light. So why do we see some stars more red, or why do we see stars red or yellow even though they have a touch of blue in it? And that's to do with the intensity of that light. And we'll show you that graph later on of what that actually means. But all you need to know for now is the higher the color, or the higher the temperature, sorry, the more blue light you'll see, and the lower the temperature, the more kind of towards the red spectrum you'll see that in. What we do know as a fact is the red colors symbolize really smaller stars and also smaller stars, or lower temperatures and smaller stars. The blue color symbolizes a higher temperature and a larger star. Okay, so there we have that. You can imagine this when we are in the lab. So using the Bunsen burner as a good example, the safety flame is usually, or is certainly the lower temperature flame, and it gives off a yellowish orange color. And also, if we add in oxygen, so if there's sufficient oxygen, we get the blue flame, which is a lot hotter. So there is sort of our own little lab correlation between the color of an object and its temperature. Notice at high temperature, we're not really looking at the chemical composition anymore. We're just looking at the amount of wavelengths exerted at that high temperature. You can also feel the infrared radiation quite a bit with the yellow flame. So let's have a look at this. So I said that the higher the temperature we go, the more blue color we see. Why is that? Because as you increase the temperature, we actually see more the greater intensity of the wave favoring to the shorter wavelengths. So that's why when you increase temperature, a star will actually become more and more blue visibly, because there's a greater intensity shift towards the blue light, and there's less intensity being built up on the red light, even though it is increasing as well, mind you. So just remember this, okay? Short wavelengths correspond to the blue end of our color spectrum, and longer wavelengths correspond with the red side of our spectrum. Here's another image to show for this, okay? So red star at 3500 Kelvin, we can have a look at it here. Why is it more favored to the red even though we have blue here? Look at the intensity. Okay, the intensity is way higher for the yellow and red star, or the red colors, than the blue and the light blue colors. So that's why our sun here appears more yellow than anything, because yellow is a greater collection, or there's a greater intensity of yellow and red compared to the blue and lighter white colors. That's where we get the yellow. There's a bit more balance there, okay, compared to our red dwarf here. Now for the blue star, there's a much bigger intensity line coming from the blue side of the spectrum, and there's way less wavelengths being emitted from the red side of the spectrum. So intensity relates to the amount of light you see. So sometimes we talk about intensity as how bright the light is. That's true, but intensity also refers to the quantity of light. So when we say the light is very intense, what we actually mean is we're seeing a lot. So the quantity of light. This could be the amount of light rays, some might say for now. But in the more quantum sense, we actually call these photons. So the greater intensity, the more photons you have. So the greater the number of photons you'll have. Okay, so that's kind of what's occurring here. If you have a higher temperature, you'll bust out more high energy photons. Okay, so that's what we have here right now. Let me just get my laser pointer back. So all objects with temperature greater than 0 Kelvin will emit electromagnetic radiation. Same with you and me. The human body is roughly around 30 to 37 degrees Celsius. We don't emit visible light, which is a good thing because we're not glowing as we walk, but we do emit infrared radiation. That's how you kind of feel body heat from a person. It's because of the radiation they're emitting. So if someone tells you that radiation is bad, to an extent, for some radiations, perhaps, but we humans do emit radiation as well. So that's the thing. We are radiators of heat. Just remember, the actual wavelength of the emitted electromagnetic radiation depends on the internal energy of the object and not characterized by the material or itself. So the higher we go in terms of the temperature, okay, we're actually not seeing what it's made of. We're actually looking at the amount of energy that's inside that object, okay? And the wavelength at which the peak intensity occurs correlates with the surface temperature. So if we are blue star, that correlates with the peak intensity that we see at 6,000 Kelvin or maybe 8,000 Kelvin. Okay, so that explains the different colors of the stars and why bigger stars are blue and being hotter, and then smaller stars being more the brown and the red. The next we have is the chemical composition. So to put it really simply, one of the questions that was asked before by one of our loyal listeners of the show, Sir Big Brain, he asked the question once, what's the difference between the continuous spectrum and the absorption and emission spectrum? Well, what you see as the colors of the rainbow, okay, that correlates to the internal energy of the atom. So that correlates to the internal energy of the core of whatever particle that you're looking at. So let's say a star, okay? So the internal energy of a star gives you the continuous spectrum. What you're looking at when it comes to the spectra in terms of absorption and emission, so absorption plus emission, that has to do with the energy that the electrons on the outer end of the star, the gases, absorb. Okay, so the emission and absorption spectrum you see is due to absorption and of energy from the electrons, and then the electrons re-emitting that energy as electromagnetic radiation. That's the correlation with this spectra. If we're looking at the continuous spectra, that has to do with the internal energy of the material. And what we mean by internal energy, we correlate with temperature. Because remember, temperature is the average energy of the system. Okay? So the continuous has to do with what's in here. Absorption and emission has to do with electron transitions. Okay, so this is kind of just repeating what we had before, but this is the main point I want you to remember, the difference between the continuous spectrum and the absorption and emission spectra. And we have to kindly thank Sir Big Brain for asking that question. Next bit we're looking at is rotational and translational velocity. This goes back to the idea of the Doppler effect. So if you recall, the Doppler effect essentially states that if an object is moving closer towards you, And this is by the fact that it is moving. Okay? So it's moving towards you. Then the frequency that you observe, whatever it be the sound waves or the light waves, will be of a shorter frequency. So if it's sound, you'll hear a higher pitch. If it's a colored form of light, you'll probably see something more closer towards the blue end of spectrum. If something is moving away from you, okay, that elongates the frequency of the wave. So you'll probably hear a lower pitch, so the pitch decreases, if this was sound. And you'll also see a more red color if this was light. So we can use that to look at if the star is moving towards or away from us, or if we just want to see if it's rotating or which direction it's rotating in. Okay? So one of the incredible discoveries we find is the Earth or the universe is expanding. And the way we know that is because we see things called red shifts. Okay? Red shifts are very incredible given the fact that when we look at absorption spectrum, so we know what most stars are made of. We know that most stars are made up of hydrogen and helium. So we should see where they are when we make the continuous spectrum. We should see a common pattern with the absorption spectra. But sometimes when we see it favoring a bit closer to the red, instead of what we previously thought, maybe the absorption spectrum we were expecting was a bit more towards this side. But now when we observe it, we see it more closer to the red side. This is called a red shift, meaning that as we were seeing the star, as I was this stick figure looking towards this star, okay, as I was looking towards this star was also moving away from me. So as it was moving away, I was getting feedback of a more reddish absorption spectra. So this is what we call the redshift. So let me just find my pen again. So here we have is a redshift. That implies the galaxy is moving away from us. And might I stress, we're saying it's moving away. We're not just saying it's far. If it's just far but not moving, we'd probably see something like this. No shift at all. Okay? If the galaxy was moving closer towards us, so velocity here, we call this a blue shift. So the light we see is more closer to the blue end of spectra. And that's really the Doppler effect we're looking at. Okay? We also know that if it's more blue, so if it's favoring way to the violet end of the visible light spectra, we know that it's moving at a very fast velocity, or either we're moving really fast towards it, or it's moving very fast towards us, or maybe we're both moving very fast towards each other. If it's on the red side, it means we're moving or it's moving further away from us, obviously, but if it's really red, obviously it means that it's implying that it's going really, really fast away from us. And this is what we call the translational velocity. So translational just means the velocity of the straight line. Okay? And so that's basically what translational velocity is looking into here. Okay? So translational just compares the spectral lines, and if there's a greater shift of the spectral lines towards the left, we know it's moving towards us. If it is like so. So redshift indicates it's moving away from the observer. And so if we look at the light sources here, we have lots and lots of reds here. That's implying that all these red stars here is probably implying the fact that it is moving further and further away from us. And so there's that. The next we have is rotational velocity. And so rotational velocity is a very simple concept to gather. Again, we're using the Doppler effect to help us understand how the star is working. If I look at one side of the star, and this only really works if the star is really close to us. If I look at one side of the star and I look at the other side of the star, let's say the light feedback or the absorption feedback I'm seeing is more blue at the top here. And then I see at the bottom, it's a bit more red. Okay? We said that red implies it's moving away from us. Blue implies it's coming closer towards us. But we're still looking at the same star. So the only way that can occur is the rotation. So how the star is rotating. If it's rotating really red on one side, it means it's rotating really fast away from us. And then if it's really blue, it means it's rotating very, very fast towards us. If you looked dead center, then you shouldn't see a shift at all. Okay? Because to you, you can't really tell where it's moving in the center. The frame of reference is just not there. Okay? So it only really works if you're very close to it. We can also find some other interesting facts for this. So if we want to look at the rotational velocity, it also has to do with the broadness of the line. So if the planet is not rotating, you have some nice thin spectral lines. If it's rotating very fast, not only do you see shifts on the two sides, but the spectrum is also broader, the absorption spectrum. Next we look at is the density of the star, so how far expanded it is. We look at the Hertzsprung Russel diagram, and we do visit this again a bit later on in this module. So the Hertzsprung diagram tells you the temperature of the star and also the luminosity, so like the brightness of the star. Our star is one of the main sequence stars, so it's kind of here. The supergiants are incredibly huge. They cover this area of the chart here. What we know in terms of the data is supergiants have very thin absorption lines, and then the main sequence stars, so the smaller stars, actually have a thicker absorption line. Now, perhaps you might be thinking to yourself, why is that the case? How do you work that one out? Ooh. Let me just adjust that. Okay, readjusted. All right. So if you can imagine, you have a really big star, and the electromagnetic radiation is moving in all parts in all directions. Okay? The thickness of the star tells you the frequency of absorption in a sense. And this makes sense. If the star is really big, so it has very low density, it means the likelihood of the EMR colliding with another atom, exciting the electrons, is going to be a lot less than a main sequence star, which in terms of size is a lot smaller, but also in terms of density, it's a lot more compact together. Okay, so if it has a high density, much more compact, it means that the EMR has a much higher chance of colliding to the atoms inside that little sun. And so that's why you get thicker bands. So that's kind of the broadness of these absorption lines tell us about the density of the object. It also tells us a bit about the pressure. If there's a greater amount or lower amount of density, that probably implies that the pressure is a lot lower as well, due to less gravity onto the atoms. So there's density there. All right, and last we have are the questions, which you'll have to have a go yourself. And so that is a basic summary of what we're looking into. Now, maybe we will just quickly glance through some of these parts. Okay, so we said that the luminosity of the star can calculate the absolute magnitude. That was one of the things I remember one of you asked is, so the color of the star, what the color of the star looks like, if we have a look here. So the color of these stars will never change, okay? They're absolute. So if it's blue, it's going to be absolutely blue. If it's red, it's going to be absolutely red. If you're stationary. So when stationary and looking at a star, and assuming that the star is also stationary, you see their absolute magnitude. So the absolute brightness of the star you see, and also the color of the star you see. But we know that most things in the world, you are moving away from the star. You are probably also, the star might be moving away from you. So if you're moving relative to each other, okay, then you see what we call the apparent magnitude. And that's where the Doppler effect comes to play. If you look into a really distant star, it might not be purely red, but what you get in the feedback of the brightness and also the absorption spectra, that might be slightly different because it's moving away from you or closer towards you. So there we have that. We know that if it's a lower density star, okay, we produce sharper and narrow spectral lines. Okay. Gas giants have less gravity, so lower pressure. So their spectral lines are also a lot more finer and narrow. If you match the absorption lines found on the star spectrum with the ones produced in a laboratory, you should be able to guess or make the prediction of what element is present in that star, and the relative intensity, okay, of the absorption lines indicates how much element is there. So this goes back to a bit about the chemical composition. So if we look at these absorption lines here, that also would tell us the abundance of elements in there as well. All right, so that concludes what we can learn from spectroscopy with looking into light and stars. Thank you for listening very much. I am Mr. Wong. I probably botched up that final bit, but doesn't matter. Have a good day and take care.